Morning, everyone. A very warm welcome to all of you joining us today as a part of India Space Week 2026 under the theme Space Education and Research. Today, we are stepping into an exciting field that is transforming the way we build, work, and explore robotics. From industrial automation and intelligent machines to robotics in space exploration, the field of robotics brings together engineering, electronics, programming, and intelligent systems to create technologies capable of performing complex tasks with great precision and efficiency. To take us deeper into this fascinating world, we are privileged to have Mr. Anirudh Wagle sir with us, Assistant Program Mentor, Robotics at Technical Career Education, TCE, Mangalore, Karnataka. Sir is a robotics and automation engineer whose work focuses on developing educational robotic kits, mentoring engineering students, and promoting hands on learning in robotics, electronics, and embedded systems. Alongside his professional work, he actively contributes to the Akansha Charitable Trust, where he supports the development of robotics, laboratories, and helps rural government schools students gain exposure to electronics, robotics, and project based learning. With his strong passion for robotics, embedded systems, and practical technical education, he's committed to making technology learning more accessible, engaging, and application oriented for students. We are truly delighted to have Sir with us today, and we look forward to learning from his experience and gaining valuable insights into the world of robotics and automation. So, without taking any further time, let us begin today's exciting journey into robotics. So, we are delighted to have you with us. Now, without wasting much of the time, over to you.
Yeah, thank you, Tanu, and all the organizers of this India Speak Week for having me here and for the warm welcome. So, uh, let me share my screen. Hope the screen is visible to you guys.
Yes, it's visible.
Yeah. Okay. So uh, let's start with robotics. Like, what makes a robot? Whenever we talk about robotics, the first thing that comes to our mind is not the field or the branch. We always think humanoid robot, right? So the word robot originates from the says word robota, meaning forced labor. So when I say forced labor, the thing is, most of us are afraid that a lot of jobs are going to uh, vanish because of this forced labor, who is a robot, right? So, but nothing to worry because a lot of jobs are getting created because of this field actually, and a lot of manual work, repetitive works are actually going, which can be efficiently handled by the robots. So basically, a robot is an intelligent electromechanical system. That's important. Electromechanical system that integrates sensing, computation, and actuation to interact with the physical world. So to dive little deeper into this, we have to look at this architecture. So always, whenever I speak about robots or robotics to anyone, I give this general architecture to, I present this general architecture in front of them. So this makes very simple to understand what is a robot or robotics. So I always divide this robotics into a robot into three uh, things. So one is sense part, one is think part, or we can say plan part, and another one is act part. So the sense think act paradigm is the basic building block of a robot. So sense part will actually helps the robot to sense the environment and plan to make some decisions based on the environment and to carry out these decisions To make some actuation in the environment, we use act part. So similar to how we humans work. So I'll be explaining this in the next slide. But to give a very simple example, so that in the sense part, robot thinks like robot starts to sense like the wall is 4 centimeter away from me, and then it thinks like, okay, then that is too close. I should move away from the wall, and then it acts accordingly, like it moves away, right? So to go a little deeper into this sense, think, act paradigm, we can divide this into sensors, then it senses, and then it plans, and then acts through actuators. So the sensor and actuator both are in contact with the environment. So if we think what is a sensor, sensor is nothing but a device which actually converts the physical energy into electronic signals, right? So a lot of sensors we see. In the upcoming slides, I'm going to explain you what are the sensors majorly used in the robotics and all. So actuator is like kind of ulta to sensors, we can say. So which converts the electronic signals into physical motion, actually, right? That does some actuation in the environment. So these both of the components are in contact with the environment. And plan is the module which plans based on the sensing input, sense data. So before we dive into the core robotics, the robot, understand the robot, we will first try to understand what are there in our uh, surroundings, that in our like room space and all. So let's just answer a few simple questions like whether a washing machine that is there in our household, is it a robot? And uh, Roomba that we see in our household, like Roomba is nothing but uh, what is that? The autonomous cleaners that we have, the vacuum cleaners, autonomous vacuum cleaners. So washing machine is of course not a robot, but the Roomba is robot because Roomba has the perception of your environment, your room, right? So similarly, drone controlled by a human. Whether we can call this drone controlled by a human a robot? So this is a bit tough question because drone controlled by a human, because there is this parameter which is controlled by a human. So we call it technically teleoperated. So this is also a robot like Roomba, but it has no perception. But we can call it as a semi-autonomous robot. Sometimes we can have perception in drones as well. So next we'll move to autonomous vehicles. Autonomous vehicles will have perception. It won't have a driver. We usually call it as driverless vehicles, right? So this is a robot. So industrial robot arm, it is a semi-autonomous robot we can call, because set of instructions will be given previously, and it will be having awareness about its surroundings, but still uh, there are certain limitations because of which we call it as semi-autonomous robots. So we'll move further into this. So before we understand or dive into space robotics or some complex robotic systems, we will try to understand something that is very much easier to understand when we talk about robotics. So we'll take TurtleBot 3, which is one open source robot, differential drive robot for indoor navigation. We'll take this open source robot and try to understand the basics of robotics, because taking a Mars rover or something like that and understanding robotics is a little bit difficult. Uh, but this Turtlebot 3, which makes us to understand things very easily. So I'll take this as a reference throughout my presentation to understand the robotics. Okay, so this TurtleBot 3 is majorly inspired from the Roomba. Roomba is nothing but a vacuum cleaner that we have in our houses. So it autonomously navigates all around our house and cleans it, right? So You might have seen cats actually playing with this Roomba, or sometimes sitting on top of the Roomba and navigating all around the house and all, right? So this is like, this almost acts like a human. It has the perception of the environment and it navigates by itself, right? So based on this, by taking this as a reference, we actually, I mean, the open source community has actually built Turtlebot 3 and made it open source. So we will try to understand robotics using this Turtlebot 3. Uh, yeah. So as you know, there are a lot of sensors and actuators are included in the robotics, in the turtlebot robot, as well as there is something which acts as a brain. So it's nothing but the hardware software combination, but majorly we can call it as a software. So majorly the one open source software platform that we see is ROS2. So ROS2, which powers this robots by giving it intelligence, not exactly intelligence, because intelligence will be given by a lot of modules that are there in the ROS2, but ROS2 facilitates the communication. Because when you consider a robot, if you consider a turtlebot 3 itself, you can see a lot of parts are present here. Like you can see 360 degree lidar here. You can see uh, certain things like OpenCR, which is a low-level control board. You can see single board computer, SBC, which is Raspberry Pi 4B, and you can see motors here, dynamic cell. Two motors will be there, and wheels will be there. Lipo batteries will be there. A lot of structures, components will be there. So when it comes to low-level control board, it will have its own firmware. So nothing but a software itself, but which runs in a low-level control boards. And in Raspberry Pi, we'll be having certain codes, softwares, right? So different modules will be there. Some drivers will be there, which takes the data from lidar. So to manage the communication between all these modules, it is literally tough. So we have something called ROS2. So you can see here motor control, odometry related stuff, computer vision related stuff, sensor fusion related stuff, mapping, localization, navigation, uh, teleoperation. Many things will be there. So ROS2 takes care of uh, the communication that's happening between all these components. So when it comes to robotics, usually uh, majorly the suggestion is for students that you can get a lot of hardwares like Raspberry Pi, motors, and many more things. But the software part, instead of rebuilding things or creating something from scratch, you can use ROS2, because a lot of packages required to get the perception of the environment will be already there in the open source in the format of ROS2. Okay, fine. So we will try to understand what kind of robots we have in the industry generally, and then we'll dive deeper into this software architectures and many more things. How a robot perceives the world, how it navigates, by taking the example of Turtlebot 3 itself. Before that, we'll just understand what kinds of robots are present in this world, in the industry. So, majorly, two kinds of robots are majorly available in the industries, working in this industry. So, one is mobile robots, and another one is manipulators. If you ask me, the Amazon has already deployed like more than 1 million robots in its factory, which is like almost reaching like one robot per one human worker, you know. So in its warehouse majorly. So those are mobile robots and manipulators, not the humanoids and all, because humanoids are still in the research stage. Whenever we say robots or robotics, the first thing that comes to our mind is humanoids. But actually, humanoids are uh, still not deployable. I mean, I can say in some of the regions it is in the level where we can deploy it, but in some of the regions it is not well developed. So it's still in the R&D stage, we can say. But the two of the major kinds of robots that are deployed and in which are working, and mostly we can say like in India, those are deployed. are mobile robots and manipulators. So manipulators as a cobots we can see in the industries like manufacturing industries most of the time. Mobile robots in the warehouses most of the time in the warehouses for sorting and getting some items from one of the corner to another corner, something like that. So if we go deeper into wheeled mobile robots, majorly we will see AGVs and AMRs in one section, which are mostly present in the warehouses. So AGVs are nothing but automated guided vehicles, or we can call it automated ground vehicles. So AMRs are nothing but autonomous mobile robots. So AGVs are present previously. Guided vehicles, nothing but they had some guidelines in the sense some RFID tags or magnetic guides. Through that guides these robots were moving to one place to another place. Nowadays we have something called AMRs, autonomous mobile robots, which doesn't need, not necessarily requires guides. So it has lidar and camera modules in it, so that it gets the whole perception of the environment. Sometimes it has a map. It will have a map already, so that it can go anywhere in that map without any guide. Okay, so the next thing is AVs. So this is one of the fascinating and mostly very, very interesting topic of mine. So I started my robotics journey by getting inspiration from the Waymo vehicle actually. So if you guys don't know, if you don't know about Waymo, Waymo is one of the driverless cars currently operating in San Francisco, Chicago area. Like these are uh, in America. So driverless cars, maybe more than thousands of cars are actually moving in the roads of America. These Waymo. Okay. So these are outdoor mobile robots, and AGV-AMRs are indoor. Most of the time, these are indoor mobile robots. So the major difference is outdoor. When we go outdoor, a lot of uncertainties and a lot of perception is required, and that's why this becomes costlier. And in India, it's too difficult because uh, you can see a lot of startups and industries are working on AVs like minus zero, Virya Autonomous Technologies, and all. But still, I couldn't see any of the uh, robots that are, the AVs that are going in our roads, maybe because of the traffic rules and regulations that we have. But you can see these kinds of AVs going in America. You can actually experience if you go there. So Waymo is backed by Google. I think it's a Google's Alphabet, one of the company under Alphabet uh, companies, I guess. So yeah. So other than these mobile robots, wheeled mobile robots, we have legged robots. So when the area or the environment is uneven, so in that case, you need legged robots. You can't go with wheeled mobile robots because the surface will be uneven. So we have bipeds, which are humanoid robots. You might have seen this Unitree robot, which is actually, we have seen this in IIT Bombay's festival sometimes, and in Roscons and all some conferences. These Unity robots are from China, and these are actually distributed in India as well. So used for many of the things, uh, and you can see quadruped robots which has four legs. We usually call it as robot dogs. Most of the times, we have seen this kind of robots. That the Boston Dynamics research organization publishes the videos of this, uh, right? So we have seen that, right? So then we have hexapods, which has six legs and all. So these kinds of robots are used where the surface area is not even. You cannot use a wheeled mobile robot. In that case, you can use these legged robots. It can actually go in the uneven surfaces like mountain areas and all. So most of the time these robot dogs and all used in the defense sectors and all. So in Mars rovers and all, most of the time they use wheeled mobile robots. They can also use these uh, quadruped robots as well. So other than these, we have underwater robots today because deep inside the sea, it's more riskier for the humans to go. And drones, majorly drones are also considered as robots, sometimes semi-autonomous, sometimes completely autonomous. And we have these the swarm robots, which we can see in the warehouses most of the time, and we can see that those things in the hotels as well as we have space robotics, uh, the robot specially designed for the space, for the other planets, to go to other planets and do some research related stuff. So when it comes to robots, we have to talk about different types of drive mechanisms. So the turtle bot that I showed you earlier has a differential drive robots. Most of the robots that we see in the educational area are a differential drive because the mechanism is very simple to understand, rather than directly going to Ackerman steering or skid steers or some other kind of mechanisms. So in wheeled mobile robots, we have different kinds of drive mechanisms. One is differential drive, the Turtlebot 3, which you can see this one, uh, that is having differential drive. That means it can have two motors and two motors, I mean two wheels and another wheel, which is a free moving wheel. We usually call it as caster wheel. So with this, it can move in the indoor environment. So similar but little advanced version of this is skid steer mechanism. So this is a skid steer pot you can see, which will have four wheels, uh, but it works on the differential drive mechanism itself, but a little bit of uh, drag will be there, and kinematics changes a little bit. And we have another mechanism which is called as Ackerman mechanism. So Ackerman mechanism is one of the uh, wonderful mechanism. You can see that, visualize that mechanism in your cars and all, where the drive wheels might be front two wheels or the rear wheels, but the direction will be given by the front wheels itself. So this front wheels, the mechanism is called as Ackerman steering. So these will be mostly used in the outdoor robots. Then you have tricycle model, and then you have these omnidirectional wheels and the mechanism wheels, which allows your robot to move in different angles, rather than having a simple architecture like differential drive. Uh, to get started with these wheeled mobile robots, some of the open source repositories that I want to share with you, or open source projects that I want to share with you, are one is Andino, and another one is Turtlebot 3. Uh, so bit costlier one is Turtlebot 4, but it's more advanced. So it has extra capabilities like it has a depth camera in it, so that you can do visual perception as well, like Visual Slam and all. Also, you have Tortoise Bot by Rigbetter Labs. So all these are the open source projects that students or beginners who are beginning it, I mean, who are stepping into the robotics can start with, because the hardware is very cheaper, and software is open source. Even the hardware is open source, so you can get all these uh, hardware required easily. So let's dive little bit into autonomous vehicles architecture. So to understand what are all the components are there in this. So majorly, I work in the field of autonomous vehicles and indoor navigation bots. So that I'm focusing more into these aspects of robotics. Uh, but if you start with this, you can actually scale it to I mean, you can actually jump into any fields of the robotics because the major thing is perception. How you perceive the world, how your robot perceives the world. So there might be dynamic objects that are moving in the environment all around the robot. How you actually avoid those objects while you navigate, how you actually detect them, how you track them, how you predict some of the things, all those things. So all those will be taken care by the perception block in your autonomous vehicle. So this architecture is referred from the one of the famous uh, autonomous mobile robot stack called as AutoWare. So you can go and search about AutoWare, which if you are interested to build uh, one autonomous vehicle for your campus or anything, you can actually refer to go and refer AutoWare. So once you perceive the world, how you perceive the world is because of the data that is coming from the sensors. So you can see sensors, so the sensing module is connected to a lot of sensors. So the sensing module is a software uh, along with a lot of drivers in it. So that those drivers will talk to these hardwares like lidar, camera, and GPS, all these sensors, and takes the data and gives it to the perception module. So perception module will actually do things like segregating the data and then cleaning it. All these data segmentation, cleaning, all these will be done in the perception block, and also it 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 extracts the meaningful information from that raw data coming from the sensors. So then it gives it to the planning block. So planning block will actually plans how I should I exactly follow a lane, or how should I park. All these will be planned in the planning area, planning section. So then this will be the planned output will be the data will be transferred to the control. So control module is bit of I mean it's a kind of module which is almost nearer to the hardware, so which converts these plans into vehicle specific commands. Like let's see your plan, okay, to follow these lanes, so you have to give the steering command. So the plan, whatever data information that has to be converted to vehicle specific commands, nothing but steering command or braking command or acceleration command. So there will be some package called as vehicle interface which binds this hardware to software. So it communicates between it makes the communication between the hardware and software easier. So there is another stuff called as localization and map. So sometimes your robots, most of the times your robots will have the map of the environment where it is exactly going. So inside map, your robot have to localize itself uh, and navigate. So to give an analogy, whenever you open the Google Maps, you always go and on your GPS. So what happens is you have the map, and inside map, when you on the GPS and when you click on that red color localization button in the map, it's going to show where exactly you are in that map. So that is called as localization. Localizing yourself in that map is called as localization. So even the robot has to do localization. First it has to do mapping. After mapping, it has to do localization. It has to localize itself in that map. Then if you give a goal, any of the goal, it starts planning a path, and then converting that path into actual movement commands, so that it can move to that uh, destination following the path. Right. So, yeah. Now we'll dive deeper into the sense, think, and act module. Let's see what are the sensors used in the robots, what are the actuators used in the robots, what is a thinking module, what exactly, I mean, which are the components used for the thinking module. All these we'll see. So, sensors are the eyes and ears of the robots. So, if you take humans, we guys have we people have a lot of sensory organs, right? Like eyes, we can see the world using eyes. So we have uh, the feeling of touch because of skin, and Because of tongue, we can taste. Because of nose, we can smell. Because of ears, we can hear a lot of sound, and uh, if someone says something, we can hear, right? So because of all these sensory organs, we can actually get the data from the physical environment, right? So similarly, a robot will also have a lot of sensory organs, or I can say sensory components. So those are cameras, microphones, ultrasonic sensors, inertial sensors, angle sensors, pressure sensors, temperature sensors, tactile sensors, and all. So we can divide these. Okay, these sensors are used to get the physical information, the data, physical data from the environment, right? So if we dive deeper into the sensors, we can divide this into the sensors required for perception, sensors required for motion and orientation, sensors required for position and movement. So let's dive deeper into one by one. So the sensors that are required for the perception. Perception is nothing but you're going to understand the environment. So if we dive deeper into perception, the sensors used for perception, you can see camera. Camera is majorly for the vision and object detection, tracking, recognition, and all. So a lot of cameras were used, monocular, depth cameras, and many more cameras will be RGB depth cameras will be used sometimes. So these kinds of cameras are used to get the vision. Depth cameras are used for vision as well as the depth of the any image that it is going to get. Okay, so then we have one of the majorly used sensor, which is lidar. So lidar is the full form of lidar is light detection and ranging. So lidar is a kind of sensor which has a laser sensor in it. So 2D lidars and 3D lidars majorly used for distance as well as uh, getting the distance between the surrounding objects as well as for mapping the environment. To map the environment, we can also use cameras, but most of the time we use lidars. Okay, so in Waymo also, you have seen a black color object in the top, right? That is lidar sensor. So there are different kinds of lidars like 2D lidar, 3D lidar. So how it exactly helps the robot to understand the surroundings and map. Everything will be discussed in the further slides. So we'll see other sensors before that. So something like ultrasonic sensors. So ultrasonic is used for short range distance measurement, and we use radars as well for this. IR sensors, most of the time it will be used in the AGVs. When you have a guided lines, you have to detect that line and move. So for this, it will be used, or to detect some objects as well. Then we have something called motion and orientation section, where you have certain sensors helping to understand the motion of the robot, or align its motion perfectly to the required motion actually, and understand the orientation of the robot. So majorly we have IMUs. So IMUs are nothing but initial measurement units, which will uh, have a lot of sensors like gyroscope, accelerometer, magnetometer inside it. So if your IMU is three axis, most probably it is having only accelerometer. If your IMU is nine axis, so in that case maybe gyro, accelero, as well as magnetometer is inside that IMU. Some of the IMUs in the market you can see like GY series modules, or MPU 6050, which is six axis IMU, and BNO 055 from Bosch. Some of the Extensa, some industry grade IMUs you can see. So not Extensa, Xsense. Okay. So these are the some of the IMUs you get in the market. So gyroscope, which gives you the orientation, nothing but the angular motion of the robot when you keep the gyroscope in that robot, when you rigidly attach that IMU to your robot. So basically, it gives you the roll pitch yaw of that robot. So accelerometer will give you linear acceleration along the axis of X or Y or Z. Magnetometer will provide you the heading and magnetic direction of the robot. So, to understand the position and movement of the robot, we most of the time use wheel encoders. So, wheel encoders will give you the wheel rotation and odometry. Uh, what is odometry and all will be discussed in the further slides. So, let's say you have only motors. In that case, it is quite difficult for us to understand how much the robot has moved. So, we have to always have wheel encoders which actually uh, gives us the information that how much the wheel has rotated. So also we have GPS and GNSS, which is called as the Global Positioning System. So which gives us the latitude and longitude of the robot where exactly present in the map. So GPS doesn't work properly inside the indoor environment. That's why we don't use it in the indoor navigation robots. And we majorly use these GPS GNSS modules in outside the outdoor navigation robots. So then we have linear encoders to get the precise linear displacement and all. So let's dive into LiDARs because these are the sensors majorly used in autonomous mobile robots, even in drones and all, to map the environment, majorly to map the environment. So LiDARs will be available in most of the time three different types. One is 1D LiDAR. We call it as point LiDAR as well. So 1D LiDAR is mostly used in the drones to get the height of the we call it as altitude. So altitude of the drone. So it is basically kind of a distance sensor we can call. So if you place this 1D lidar on top of a motor and rotate it, so that makes the 2D lidar. Just to basic, understand it in a simpler way, I told like this. Okay, so the procedure is literally it's little complex than that, uh, but you can think like that. So 1D lidar is rotating. uh, that's what you can think when I say 2D lidars. Okay, so 2D lidars will have 2D perception of the environment. So using this 2D lidars, you can actually create 2D maps of the indoor environment or even outdoor environment, but it's quite difficult to use 2D lidars in the outdoor environment. So when we do outdoor navigation robots, we don't rely only on the 2D lidars. We also use 3D lidars. So these 3D lidars will give you a point cloud data. So a points of information about the surroundings. So like you can see in the picture, like we are able to get the 3D map. You can see the trees or in front the objects and all, right? So 3D lidars will have vertical frame of field of view, also a horizontal field of view. Usually horizontal field of view of the 3D lidars will be 360-degree and vertical will be somewhere 40 to 60-degree. Sometimes uh, more than that will be also there. So if you take like humans will have a field of view of like horizontal field of view of maybe somewhere around the 180 degree. No, not even 180 degree, I guess. So somewhere around 180 degree, and the vertical field of view is somewhere around 90 degree. But we don't have 360-degree horizontal view, right? But 3D lidars or 2D lidars can have that, so they can see what is going on behind them as well, right? So this is about lidars. And let's talk about a little bit of encoders as well, because this is one of the major sensor component that we use in mobile robots. So as I said, encoders are the sensors that are attached behind the motors. So you don't simply power the motor and control your robot. You also get the feedback from the motor that how much the motor shaft has actually rotated because of this encoder modules. So majorly we see magnetic encoders and optical encoders. So this is a kind of magnetic encoder which has one magnetic rotor disc, okay, in it. So this is attached to the axle, motor's axle. Okay, you can see here a magnetic disc is actually uh, attached to the axle of the motor. And also you can see two Hall effect sensors to sense the magnetic disk, right? So the movement of the disk. So how this will be calculated, all those things we'll we'll understand in the next slides. Before that, we'll understand what is an optical encoder. So if you see an optical encoder, this looks something like this. You will be having your axle somewhere here, and you will have surrounding to it, you will have an optical one disk, which will be having lot of slits, lot of openings here. Then one side of the disk, you will be having light source. You can call it as a photo emitter. And another side of the disk, you will be having detector. So which is a photo detector. So this light will be passing through the slits and reaching this detector. So whenever this disk rotates, so let's say if I rotate this disk once, fully one rotation, uh, at that time I'm going to detect the light, uh, the number of slits, how many number of slits will be there, right? That much number of times I'm going to get the light, so that I can understand for one rotation these many counts I'm going to get. So counts we are going to get when the light goes through that slit and it will be detected by the detector. So let's say the detector detects once, then that will be considered as one count. So how many slits will be there? That many counts we are going to get when we rotate the disk fully once for one rotation. Okay. So the one rotation of the disk is possible when you rotate the axle fully once. So because of this, we are able to get how many, we are able to understand how many times our uh, axle has rotated. And as we have the wheel's radius with us, we can actually find the circumference of the wheel, and then we can calculate how much distance our robot has moved. This is the general uh, odometry that you see in your vehicles as well. Your vehicles, most of the time, it will give you how much kilometers you have moved, right? This is because of the odometry that your vehicle gives. So let's understand odometry as well. Before we dive into odometry, we'll just understand how the magnetic encoder works. So so you can see here, the disk is divided into six parts: south, north, south, north, south, north. And you have two Hall effect sensors, one and two. So every 30-degree, one of the sensors is going to detect north or south. So if it detects south first and north next, so the sensor is going to assume that uh, the motor is rotating in clockwise. If it detects north first followed by south, then sensor is going to detect it as counterclockwise. So, so each time whenever it detects north or south, it is going to give you a count that is one count. So when it fully rotates, you are going to get the total count of it, right? Okay. So yeah, let's understand odometry. So odometry is one of the major concepts in robotics, using which you are going to understand where exactly your robot is, how much it has moved. So you can see here. So initially the robot was having 0, 0, nothing but the counts were 0, 0. So robot has moved a little bit. You can see the counts, the encoder counts are 50, 50. Both the counts are 50, 50. And if you move a little bit forward, so you can see 100 and 100. These are the counts we are going to get. Let's say our encoder has 100 openings in its encoder disk. So we have an optical encoder. Let's say we have an optical encoder. So one full rotation is going to give us 100 uh, 100 counts, right? So when we read that encoder, now let's say we are going to get 100 counts. So how to convert this into distance? So we already know that 100 counts is equal to one rotation of the wheel. So one rotation of the wheel means the wheel has moved, or the robot has moved, the circumference times the distance, right? So if we know the diameter or radius of the wheel, we can, of course, by using the uh, formula 2 pi or 2 pi r or pi d, we can find out the circumference of the wheel. So one rotation of the wheel is nothing but circumference times of distance we have moved, right? So if we get to know, okay, 100 counts are uh, sensed by the encoder, that means one rotation is happened. So that means circumference times the robot has moved. Let's say we have got 1,000 counts. That means 10 times, I mean, the 10 rotations that robot wheel has already completed. That means, so 10 rotation into the circumference. That much of distance it has moved. So it becomes very simple to understand how the odometry works, right? So if your robot rotates right side, you can see 40/80. So one of the encoder is going to give more counts, and another robot is another wheel of the robot is going to give the less count. So you have different formulas to apply here and understand this, of whether the robot has moved right or left based on the difference in its encoder counts. Okay. Yeah, that's what about the odometry. So now we understood the wheels are going to give that encoder counts, but that finally we will convert those encoder ticks or counts into x, y, and theta. So using this equation, we are going to convert those things into x, y, theta. So why x, y, theta is because your robot, I'm talking about turtlebot 3 or any of the two wheel differential drive robots. So these two wheel differential drive robots, your Roomba or turtlebot 3 or any of these robots, will be always moving in the 3D environment, but I can see 2D environment. Why? Because it's not flying in the Z axis, right? It's not moving in the Z axis. Z axis, uh, which faces the upward, which is in the upward direction. So it's not like a drones. It's not moving in the upward direction, right? Only it is moving in the 2D environment, right? So 2D environment, when it comes to 2D environment, we always uh, we use Cartesian plane, right? X and Y. So to understand where our robot exactly is present at the current time, we always use X and Y, its position, right? So we always have to convert this encoder counts into X and Y, to understand where exactly our robot lies in that 2D environment. So that to convert from the encoder ticks to x and y, uh, I mean its position, you have to apply differential drive kinematics and odometry. So this is a bit of math and a lot of uh, computation you have to do for this, which is basic. So you can understand about this by going to Medium. There is a wonderful article written by Nabi Ahmed. You can go and search about it. Also, to understand robots, now we understand the position of the robot because of its x and y, like x coordinate and y coordinate. So let's say we want to understand the robot's orientation, whether it's facing to which direction. So if you want to understand this, so we should get the theta. So all these x, y, theta can be calculated. Uh, can be calculated using inverse kinematics, using the encoder pulse data. Okay. So this is what I explained in the last slide. So initially your robot will be having in a 0 0 initial position. X will be 0. Y will be 0, and the theta, its orientation is somewhere, let's say 45 degree in this case. So you are going to move the robot, and now the robot is somewhere, uh, let's say x is equal to 5 and y is equal to 4, and theta is same. You can see theta is still same, 45 degree, right? So because of this representation, we can actually understand the robot's local position. Okay, right. So we have understood how sensors are going to give the data, how to take the sensory data, and uh, how those are going to help the robot understand where exactly it is using odometry related stuff. So there are other things that sensor does, like using lidars, it gives the perception to the robot, and many more things will be there. So now let's talk about actuation. We'll cover the think part little later. So actuation is, once you give the sensor data, once the robot understands the physical environment, it starts thinking what to do next, and uh, converts. It generates some actions. So those actions will be done by using motors and such stuffs. So if we compare robots to humans, humans have legs and hand and wrist, many more ankles, certain joints and links stuff, right? So similar things will be there for a robot, which are actuators to execute some decisions and control the hardware. So we have a lot of actuators like DC motors and servo motors, which gives a precise angular positioning. DC motors are the normal motors which everyone has. Everyone understands, I guess. But the servo motors, which are used in the uh, scenarios where you need precise angular positioning, right? So stepper motors will be there in some of the places. In some of the robots, you can see BLDC motors. Majorly, BLDC motors are brushless DC motors used in the drones. Okay, so then you have linear actuators. So for certain works, majorly we can see this in hydraulic systems and all. So then you have hydraulic actuators and pneumatic actuators and solenoids. So these kinds of actuators you can see in the robots. So now we have seen certain sensors and certain actuators. Uh, Between these sensors and actuators, actually you are going to see a lot of computation going on, and the computation will be handled by the some computation units like Raspberry Pi or Jetson. So when it comes to industry, they will be using industry grade computers and sometimes Jetsons, high end Jetsons and all. But for a hobby person, it's preferred to start with Raspberry Pi kind of simpler single board computers. Raspberry Pi is a computer. It's a simple computer, I can say, similar to computer, uh, which helps the robot to think. Uh, which helps the robot to think, like a lot of sensors and actuators are actually connected to these Raspberry Pis. Okay, so the major computation, the software is running in this Raspberry Pi. So it's similar to your computer. It can have a OS. Majorly, we flash Ubuntu based. Linux based operating system in the Raspberry Pi. So it has many models like Raspberry Pi 4B, Raspberry Pi 5. 5 is the latest model. I think if you're a technical person, you might have heard that the price of the Raspberry Pi has doubled, and maybe more than the double. It has went from 2025. I guess, right. So previous year, last year it used to be 4,000 or 5,000 somewhere for the basic model, which is 4B 4GB RAM one. So now it comes for somewhere around 11,000. But still, it's one of the good microprocessors which most of us can afford to start with the robotics. So it has a mobile processor which is ARM Cortex A series A72 or 76 processor in it, which is of quad core, and uh, the clock is very good, like 1 gigahertz clock it provides, and quad core processing, so it can do some multitasking. So you can literally deploy, have a general purpose operating systems like Ubuntu 22, 24, its server versions or desktop versions in it. And it has a lot of input output ports like GPIO pins, as well as USB Ethernet ports and all. So you can actually integrate high-end LiDARs, cameras to this module. Then you have Jetson modules for higher computation. This is from NVIDIA. So for high computing, you can use Jetson modules as well, because there is a lot of flexibility in it, like when it comes to memory and all. So it allows you to upgrade your RAM or the SSDs, put SSDs into it, so that you can do a lot of AI related stuff uh, much more easily in Jetson compared to Raspberry Pi. So, but yeah, I took example of TurtleBot 3. It uses Raspberry Pi 4B. Okay, so even the TurtleBot 4 version, which is like Roomba, will also use Raspberry Pi 4 version. But the Roomba exactly that you see in your homes and all, houses and all, so those might not use Raspberry Pi in it, might use their own custom processors and controllers. So, mm, robot will not only have microprocessors in it, also it will have microcontrollers. You might ask me why microcontrollers when you have processors, high-end processors in it. So, before I answer that question, let's understand what are these microcontrollers. So these comes in most of the times. These will be covered in the embedded system classes or embedded system theme. But I'm bringing this in the robotics lecture because embedded system is one of the major stepping stone to start your robotics itself. Because at the end, whatever you make in the software in the simulation, you have to deploy it in the hardware to tell it as a robot, right? So hardware is nothing but these microcontrollers and microprocessors and all those stuff, right? So microcontrollers usually have a bit of less memory and uh, but the software layer in these microcontrollers are very less, the layer. Okay, if you take Raspberry Pi, you will be having a OS layer. So whatever the programs you run there, so a bit of delay is going to affect you there. But the delays are very less in these microcontrollers because these are bare hardware on top. You directly write your program. So the time critical tasks like motor control, getting text from the encoder, you should not miss some of the things there. That's why what you do is you actually integrate the motors, encoders, all these sensors and actuators to the controllers. Okay, these controllers because they are more real time compared to processors because of the the software abstraction layers. Okay, so we generally use STM32 or Arduinos for the beginners and ESP32s and all. So these will have Cortex M series chips in ICs in it, so which does real time tasks and all. So uh, these are for the real time things. So that's why we have microcontrollers as well as microprocessors both in a robot. Right. So I said we are going to use processors as well as the controllers uh, in our system. So how are we actually distributing our work? So if we take example of TurtleBot 3, uh, the computing is distributed uh, because we can't give the whole task to one of the processor, right? So what we do is we divide the tasks. Certain tasks will be run in the remote PC, the PC that we are using. Certain tasks will be running in the single board computer, which is Raspberry Pi. Certain tasks will be running in the low level computer. When whichever the robot you see, you can identify a lot of processors, a lot of controllers, all are working uh, uh, together. So this is possible because of the technology called as distributed computing. So to do this distributed computing, actually the ROS2 will help us majorly. So that's why we use ROS2 here. So I'll just explain about ROS2 in the latest slides. Before that, I'll just tell you uh, what are the software modules. Whenever we say the brain of the robot, we can't just wind up with the hardware like her Raspberry Pi or Jetson. We also have to talk about the packages, the software packages that are running inside that brain. So the software packages that are running inside the brain like Raspberry Pi are these whenever the application is ROS2 based. So Nav2 is one of the software package that helps us to navigate, the robot to navigate. Slam Toolbox, which helps robot to localize in the environment, map the environment, all this stuff. So some sensors will be there. Its driver code will be there inside your SBC. Also, some controllers will be there. So controller is the package where you have the kinematics, differential drive kinematics, and the joint broadcaster, uh, which takes care of broadcasting the joint states. So let's see, your robot has moved a bit. So that means its joint has moved actually. So now the joint state is changed, right? So the change in joint state will be monitored by this joint broadcaster. So diff drive controller is nothing but it is kinematics of that robot. If you have a Ackerman steering robot, then you will be having Ackerman controller. If you have some other robots, its kinematics will be there in the controller section. So bring a package is one of the software package which takes care of launching all the sensors related code, perception related code, hardware interface code, all these things, right? Okay. So this is a basic architecture of mobile robot, which is a software architecture. So let's dive into differential drive architecture because we are looking at the Turtlebot 3. So how we can actually move the Turtlebot 3? So I said it's a differential drive architecture, so mechanism. So when we say differential drive, we always see two-wheel robots. So two wheels are used to drive the robot, and another wheel which is used to it's this is the third wheel is like free wheel. It's kind of having free movement. We are not going to control that wheel, which is caster wheels. So if you want your robot to move straight, what you have to do is you have to your control your motors in such a way that the direction of the motor will be in the same direction and the speed will be same. So in that case, you can actually drive the motor forward. If you do it in ulta, uh, way, it is going to drive backward. Like the direction of two wheels are anti-clockwise, as well as the speed will be same. You should not make changes in the speed of two wheels. So in that case, we can come back. The robot can come back. So if you want to turn your wheel left, you can turn it in two ways. The first way I'll tell you that uh, the left wheel give speed to the left wheel a little and give more speed to the right wheel. In that case, you can rotate the robot to left side. If you want to rotate right side, give more speed to the uh, right wheel and no left wheel, and to the right wheel you give less speed. So in this case, you can turn your robot to right side. So this is where you don't touch the direction. Direction will be forward itself, right? Now, if you want to do a pivot turn, pivot right turn or pivot left turn, what you have to do is you have to play with the direction of the wheels. So if you make the direction of one of the wheel front and one of the wheel backward, it's going to turn at its position itself, that we call it as pivot turn, to right or left. So that kind of rotation is also possible. So but as a human being, we can't actually guide our robots like okay, your left wheel should be moving in this direction, this speed. Your left wheel or right wheel should be running in this speed, this direction. We can't every time we can't tell this. So what we can do is we can tell that our robot should go in this much linear velocity. uh, uh, if it is positive velocity forward, if it is negative, then it's going to uh, going backward. And also, if you want to uh, turn that robot, we can just command it like, so you have to take this much angular velocity about z-axis. So basically, how we can instruct our robot to move is by giving linear velocity along x-axis and angular velocity about z-axis. So please remember linear velocity along x-axis and angular velocity about z-axis. So linear velocity along x-axis to move the robot forward or backward. So angular velocity about z-axis is to rotate the robot like about its z-axis. Okay. So with these two commands, we can actually control the motion of the robot. But robot won't understand this x and z axis, linear velocity along x and angular velocity about z axis. So what we have to do is we have to apply some differential drive kinematics and convert these linear x and angular z to wheel specific parameters. So what the robot actually understands is, whenever I say robot, the motors of the robot is PWM signals, pulse width modulation signals, nothing but some electronic signals, right? So to convert these linear x and angular z to electronic signals that are specific to left wheel and right wheel, we have to use differential drive kinematics. In the previous slide, you have seen differential drive kinematics controller will be there. So that will do this kind of task. So whatever we give linear x and angular z will be converted into wheel specific. Like in between, it will be converted into angular velocity, linear velocity of left and right wheel. Then finally, it will be converted into PWM signals. So which is nothing but the power that we are giving to the robot. Yeah, let's understand how a robot actually navigates through certain environment, how it actually goes through environment, maps it, how it exactly navigates. So let's say we have a robot and two obstacles in our room. First, we teleoperate. Teleoperation is nothing but we control the robot. We move the robot. So we are moving the robot somewhere like this. You can see we are moving the robot. So now I have moved the robot. So now I have the whole perception of the environment. Now I give the destination that this is the destination, the green color position you can see. I say that this is the destination of the robot. I instruct the robot that your destination is here. Now you have to go without my help. So what robot does is it plans a path from its initial position to the destination. It plans a path. So once it plans a path like this, so the planning of path is nothing but it uses some algorithms like A star, modified A star, or Dijkstra's algorithm, or RRT star. Many algorithms will be there to find the shortest distance between 2 points. So using these algorithms, this robot will plan uh, how it can move. So it uses some packages called as nav2 for navigation. For mapping, it uses slam toolbox and all. So once it plans the path, it starts moving. It starts following that path and finally reaches that destination. So yeah, but uh, these are all the stuff, whatever I said, like odometry, differential drive, uh, always monitoring the joint states of the robot or mapping the environment, localizing the robot inside that environment, navigating. When I say navigating, planning a path and then executing that by moving in that path. All these modules, to construct all these modules, it becomes very complex for us. Sometimes these were already created by some of the open source giants, so we can reuse those stuff for our projects instead of rebuilding certain stuff. We can actually use these stuff, right? So to use these stuff, we have to actually uh, use a special tool called as ROS2. ROS2 is nothing but robot operating system, which helps you to develop the application, software application for without rebuilding certain stuff from scratch. So let's understand how the ROS2 environment is about its structure and all, its architecture. So how we can utilize this ROS2 to build a robot later on. So the major motto of the ROS2 is that don't reinvent the wheel. Instead, uh, just improve it. So yeah, in ROS2, first we start with simulation. We try to build the CAD model of robot and we try to simulate it in the virtual environment and test our algorithms, and then we finally deploy it in the hardware. So before we deploy it in the hardware, we always simulate it in the virtual world. Otherwise, what happens is uh, sometimes our algorithms might not be proper.
Sir, you're not audible. Your mic is mute, I guess.
Hello, Hello. Is there any problem? Uh, I can hear someone's speaking. I couldn't understand uh, any problems from my side. Hello. I hope everything is uh, proper. I'll just continue with the slides. So yeah, I was saying that you have to simulate first and then you deploy that code in the hardware. So uh, yeah, so we use certain simulators called as Isaac Sim or Gazebo to simulate our robot initially and then deploy it in the hardware. Uh, so before we dive into all those topics, let's understand what is ROS2. So ROS2 is a distributed robotics middleware framework used to build modular, scalable, and real-time capable robotic systems. It's a collection of open source libraries, tools, and packages that helps you to build your robot software without writing everything from the scratch that I explained it in the earlier slides, right? So in ROS2, we have certain distributions. So we have some distributions like Humble Hawkswell, Helisco, Kilted Kaiju, all these. So these are some of these are long-term supported distributions, and some are not for long-term. Like they are just for very short term. I mean, to test some of the features and all. So beginners can start with Jazzy Helisco because that is the stable version currently, and also Humble Hawksbill. But it's going to get end of life by 27. So I prefer beginners. You can start with Jazzy Helisco, or there is another new distribution coming, but it might not be stable as a Jazzy. So you can start with Jazzy. So majorly you need to have Ubuntu 24 OS for this to work on all these. And the major advantages of ROS2 is some standards and conventions are followed so that the code that you write can be, the whole system can be deployed in the industrial environment because nowadays it is standardized and it is under some, it follows some conventions. So that is the reason we can use it in the industries if we develop certain things using ROS2. So then sensors and hardware are plug and play as long as the manufacturer provides the ROS drivers like LiDARs, and you don't need to write the drivers because manufacturer provides most of the time. So you can directly plug and play with it. Uh, so a lot of already existing packages that do a wide range of things required to start working with the robot. No need to reinvent the wheel. So a lot of packages are already there. You can just use it for your system. So distributed architecture, so you can use multiple computers, computing units in your robot, uh, which works by talking to each other. So that will be facilitated by ROS2. So then ROS2 is actively developed and uh, kept active by NVIDIA, Sony, Canonical, all these big companies, and a lot of developers from all these companies will be using ROS2, majorly NVIDIA. And ROS2 has a good community, ROS Discourse and Robotics Stack Exchange, so that any of your doubts will be clarified there. So you will get a lot of robotics enthusiasts there, and you can share your development informations with them, and also get some doubts clarified there. So slowly it's becoming a standard framework for the robotics software development. So that's the reason I am introducing you with ROS2. In ROS2, the modules like navigation, localization, all these will be organized into ROS2 packages. So this is the mechanism which takes care of organizing uh, the code. Okay, so that's what if you are going a little bit deeper into ROS2, you can go and explore about ROS2 packages and all. I might not be able to cover in this session, because I'll try to give general introduction. So basically, if you are still confused, what exactly is how exactly ROS2 is going to help us? So it is because of its communication architecture. It has majorly three kinds of communication architectures, which is one is pub sub, another one is service client, another one is action service client. So you can see each and every code that you write inside the roster environment is divided into nodes. So node is nothing but a piece of code. So a node can be a publisher, a node can be a subscriber. So publisher node might be like, I can say a lidar node can be a publisher, which is constantly publishing the lidar data to a certain topic. So whoever, like mapping module or localization module, whoever wants this data, they have to subscribe to this topic and get the data. So this will be facilitated by the ROS2. So not only this PubSub, whatever I explained, also you have certain other communications like request response, which can be facilitated by using the service client. So there will be a server, there will be a client. So client asks for some service, request for some service, and the server will do that task and give the output to the client. So that is request response kind of communication facilitated by the ROS2. And then you have action servers and clients, which is like you have a very big task, so you ask some server to do that. Your server will constantly send the feedback to the client, and finally when you finish the task, it is going to give the output as well. So that is another kind of communication that is facilitated by the ROS2. And your robot will be represented using URDF inside the roster environment. So URDF is nothing but Unified Robot Description Format. So when building a robotic system, multiple software components need access to the robot's physical properties, such as its shape, size, mass, joints, and coordinate frames. Because the robot should be self-aware first. First of all, it should be self-aware. Then it should get the perception of the environment. First it should be self-aware that okay, it has a joint, it has a base, all those things, right? So it should be knowing its physical properties first of all. So this many software inside your robot needs this physical information of your robot. So this will be given using URDF, Unified Robot Description Format. So to keep this information consistent and centralized, ROS uses common robot description format called as URDF. So this file defines the robot's structure in a standardized way, allowing simulation, visualization, motion planning, and control systems to reference the same model. So you can see here, robot model, CAD model is uh, fed into ROS2 environment, and we are visualizing using a tool called as RViz, which is ROS2 visualization. You can see its frames are actually tracked here. So using TF. So also robot has uh, its joint frames, and this will be tracked and taken care by the TF2 module. So if your robot is moving in certain environment, that means actually its joints are moving. So some mathematics is happening there. So math is happening there. Some joints are moving means some frames. Some joints are moving in it with reference to some x-axis or y-axis or z-axis continuously. So this will be monitored continuously by the TF2, calculated by the TF2, which is transform frames library in the roster. So now we understood a little bit about robots odometry, about its kinematics, like differential drive kinematics, about its frames, like how the links and joints will be there, how the TF2 will be there, how we are going to feed the robot's physical model to it and all. So now let's understand how robot maps an environment and localizes itself inside that map. So it maps the environment and localizes using SLAM technique. SLAM is nothing but simultaneous localization and mapping. So the content for this, the information that I'm showing you is majorly referred from the Henke Robotics GitHub repository. So I would like to thank them and mention them as I'm using it here. So without Slam, you can see robot, if our turtle bot or Roomba is cleaning the room, it starts cleaning the room randomly because it's not aware of the room, right? So let's say if we are using Slam, so then it will be having the map. When you have the map, it can actually optimize its tasks. It can actually do it in a proper manner. It can plan its path in that map properly. You can see cleaning while understanding the room's layout is much more efficient. It's going efficiently compared to without having a map, right? So that's why having map is very important. To have to get the map, you need to use the technology called as SLAM. So mapping is a process of creating an internal representation of the outside environment by making use of the data that is gathered from the observation sources. The observation sources are sensors. So without mapping, the robot would have no internal representation of the outside world and would not be able to take intelligent actions that would interact with the environment in a meaningful way. So localization is the process of estimating a robot's position and orientation. I said position is nothing but XY in terms of differential drive robot, and orientation is the theta of it within a known map using sensors data. So the sensory data that are used for the localization are LiDAR's data and majorly the encoder's data using a technique called as odometry. So without localization, a robot may have a map of the environment, but it would not know where it is exactly inside that map. So SLAM is the process of creating or updating of map of an unknown environment while simultaneously keeping track of the robot's location within it. I mean, you do mapping as well as localization simultaneously together. So before we understand how exactly the process of SLAM goes, we have to understand certain parameters like laser scan. What is a laser scan? What is odometry? What is postgraph, scan matching, and occupancy grid? Certain topics are a bit uh, only for roboticists, but certain topics can be, I mean, it can be understood for by everyone. So we'll first understand what is a laser scan. It's an array of distance measurements visualized on a two-dimensional plane. When it comes to 2D lidars, when you have 2D lidars, it's an array of distance measurements. You will get it in two-dimensional plane. So usually and best obtained from the laser-based sensor, which is lidars. So can also be generated using depth measuring sensors like depth cameras and all. But you can see here how we can get the laser scans using a 2D lidar. So you can see a lot of laser scan data here. So using which we will get the laser scan. So this is a one parameter we need to do the SLAM. Then odometry. I explained odometry in the initial slides where you have your robot like this. It's X position 0, 0 and 0 degree is the orientation, X, Y, theta. And then you move it to 1 comma 1 comma and the orientation is changed to 30 degree. Then the goal position might be somewhere around 3 comma 3 comma 45 degree. It has to move there. So when it moves from 0 comma 0 comma 0 degree to 3 comma 3 comma 45 degree, which is goal position, it actually travels through a path and the path is divided into these X, Y, theta points. So uh, how you exactly get to know its position is because of odometry. So odometry is given calculated using encoders data. Okay. So the estimation of a robot's position and orientation is nothing but odometry, and you get position estimation as well as you get orientation estimation. So what multiple types of odometry will be there. Wheel-based odometry, where we generally use wheel encoder ticks to understand the odometry. I mean the position of the odometry. I mean position of the robot. And also we have visual odometry and inertial odometry. Inertial odometry where you use IMUs to understand the movement. So those things. Uh, Next, we need to know about the post graph. Post graph is like based on the laser scan readings, different frame of the laser, you are going to understand the location of the robot. So it's quite difficult to understand, but one of the major concepts used to localize the robot, post graph localization. So then we have scan matching. You match the scan that the lidar has done in first frame to the next frame. So you match this and you try to localize your robot. So that is scan matching technique. And then you have uh, another parameter, which is occupancy grid. So you should understand this occupancy grid before we build map. So occupancy grid is nothing but a 2D grid-based representation of the outside world. So it is built with a certain cell resolution based on the size of the robot and the SLAM configuration. Easy to understand, each cell holds a value. The value tells whether that cell is free or occupied or unknown. So map is represented as the occupancy grid map. That means the map is actually divided into uh, occupancy grids, the cells. It will be divided into occupancy grids. So, and each and every grid will be given with certain values. So, from -1 to 100. Let's say, let's take one grid here. You can see a lot of grids here, right? So, let's take one grid here. So, if it is -1, that means the unknown space. Unknown space in the sense the lidar scan has not reached that space actually. So, if that grid as having the value 0, then free space. That means the robot or the lidar has identified that space as free space. It has recognized, I mean, it has understood, okay, it's unoccupied space. So you can see black cells here. Those are given with the value 100. That means, oh, that those are the occupied space. That means the robot has understood, it has explored that area and it understood it's occupied. So majorly, robot thinks whether the area is explored or not. If it is unexplored, -1, unknown space. So if it is explored, then whether it's a free space or occupied space, that will be given. So these notations will be given based on, I mean, laser scan data, and it will be represented using the values like -1, 0, 100. Fine. So the mapping process goes like this. So receive a new scan from the lidar, receive odometry from sensors to estimate the robot's pose, save the current scan and estimated pose to the pose graph, perform scan matching, then update the built occupancy grid based on the current pose and scan. As we visit previous locations, we must use the pose graph and sensor reading to perform loop closure detection. So using all these scan, odometry, pose graph, and occupancy grid, the robot is going to do mapping. So when you do the mapping, you have to teleoperate it. I mean, you have to operate the robot first, and it starts mapping. Once it has the map, you feed the map to the robot and leave it to explore, leave it to navigate autonomously. So this is a person who is Steve McKenzie, uh, the major person behind this Nav2 and Slam Toolbox packages, who build these packages for ROS2 developers to use this to navigate easily, to map the environment, to localize the robot inside the environment. So certain times you can see very bad map will be generated because your odometry is not good, or some localization is not happening properly, or scanning is not happening properly. So always better to have a good map so that uh, next navigation will be performed very efficiently and easily. So a lot of challenges will be there when you do mapping. So the objects will be moving sometimes. Uh, Doors and trees, all those are non-static features. So because of those, uh, changes will be there when you map. Certain things will be in certain order, and when you navigate, they will be in other order. So when you have a larger environment, you need to collect the data, map data, and keep it. So it becomes literally hard. I mean, you need to have a larger memory, and CPU constraints will be there. So sensors data limitations will be there, like noisy data, sensor range, sometimes bad calibration. This all affects the mapping. So now we have the map, and our robot knows where it is exactly present inside that map. So now how to do navigation? Let's say we have given a destination. How to go from one position to that destination position? This will be done by navigation. autonomous navigation, the process of moving a robot autonomously between two locations in a 3D space. So this is done by planning a path and then executing the path without any human intervention. So moving in that path without any help of the human intervention, help of the human. The planning is done by a planner component. The execution of the plan is done by a controller component. So this planner component, controller component, actually given by the nav2. So nav2 is one of the framework that provides all these planning, control, perception, localization, all these components, so that our robot can easily move to one any of the locations. So this is the architecture of the nav2. I'm not going to explain this in depth, but just you can see that you have a controller server to convert the plan into actions, and you have planner server to plan the path, behavior server, which takes care of a lot of modules here. We're using a behavior tree, and the smoother server, which corrects the, I mean, smooths the your path that is planned. So collision monitoring, avoidance, waypoint following, many things will can be done using nav2. So before we use nav2, the robot must have odometry from the wheels, correctly configure TFs, nothing but the transformations, each and every joints information. Sensor should be there and properly configured. Correctly calculated robot footprint should be there, and a map. Occupancy grid must be built beforehand using a SLAM package. So now to parameter configuration should be there. So in nav2, we represent the environment, the map, in different ways like static map, global cost map, and local cost map. So we'll be having a static map, global cost map, nothing but it will be having the information like the where exactly obstacles are present, where exactly high cost will be there, where exactly low cost will be there. So it divides the map area region into high cost and low cost. So the robot should understand that it has to always go in the low cost area. High cost means there is something obstacles or it's an area nearby obstacle, so it should not follow that. It should not move in that environment. And local cost map is the cost map surrounding to it, because always you can't rely on global cost map. So it also has a local cost map. So uh, so that's a general idea of cost map. So we'll be having a first static map, which is the same map that I explained, the occupancy grid map. Then global cost map is something like this, provides a long-term global view global view for path planning over the entire environment. So if there is some dynamic changes, it reacts to the changes in the environment using live sensor data, acts as a memory of dynamic obstacles. So it also handles dynamic obstacles. And uh, yeah, this is actually local cost map. There is a bit of changes here. So offers a short-term detailed view of the robot's immediate surroundings for real-time obstacle avoidance, and focuses on short-term obstacle avoidance, continuously updates with the live sensor data like lidars and cameras, and works in the robot's coordinate frame like base link. Then now to also provides a localization component, which is localization using AMCL, Adaptive Monte Carlo Localization. So this is a probabilistic localization module which estimates the position and orientation of the robot in a given known map. So you can use AMCL as well to localize your robot. So how does the path planning works in nav2? So we have two path planners. One is global path planner and local path planner. Path planner. So computes a collision-free path from the robot's current position to the goal. So goal is given by humans. So the global path planner will plan a path, global path from its initial position to the goal position. Uses the global cost map to plan paths around the obstacles. Also, the common algorithms used are A star, Dike stars, and now FN. So these are the some of the algorithms used to plan this path. You can see here there is a AMR here, and you can see in between obstacles, and you can see goal. So it plans a global path. Let's say suddenly obstacle comes in between that path, then it changes its local path. I'll show you the local path later, local path plan in the next slides. So local path planner changes its path and it avoids the obstacle, and again it starts following the global path itself. So this is local path planner idea. So where it is also known as controller follows the globally computed path by moving the robot, uses the local cost map to avoid dynamically detected obstacles, make sure that the robot's movements are feasible, ensure that the velocity commands do not exceed the hardware limits. So it ensures the velocity commands do not exceed the hardware limits. So actually, whatever the velocity that it is planning is not actually uh, above the hardware limitations like the motor limitations. Smoothens the trajectories, shortcuts for sharp corners and all. So drive system constraints, for example, differential holonomic increment drive system, some constraints will be there. So it handles all those things, the local path plan, avoids obstacles and all. So behavior tree is one of the uh, structured and flexible way through which now to actually performs all these multiple tasks. Okay. So Nav can also provide certain stuffs like autonomous docking, collision monitoring, map filtering, all these things. So these are the things. So using Nav2, we understood that we can do autonomous navigation, obstacle avoidance, and many more things. As well as now we have gone through a turtle bots or a differential drive 2D, not exactly 2D, a simple differential drive robot, indoor robot, how it works and how we can build and all those stuff. A little bit about manipulators, because I said that mobile robots and manipulators are the major two robots, kind of robots that we use in the industry and academia uh, today. So so let's talk a little bit about manipulators. Manipulators are majorly used in the industries for pick and place or inspection related tasks, sometimes for welding and all those certain tasks. So today you can see Lay Robot S10 SO101, which is a wonderful manipulator you can start with learning. You can start learning with this. So which has a leader and follower app. So you can do a lot of stuffs related to physical AI, and also you might have heard VLAs, vision language action models. Today, robot I mean, the AI is able to give action as an output. So those things and all you can try with these manipulators, even with the mobile robots. So manipulator works with the idea of kinematics, forward and inverse kinematics. Let's say you control its joints and get its end effector's position, which is called as forward kinematics. And let's say you give a position of the end effector, then it calculates its joint angles, positions, whatever by itself is called as inverse kinematics. So these are the technical areas which you have to dive into uh, if you want to work in manipulators area, manipulators domain. Uh, so with this, we'll try to discuss a little bit about industrial robotics science. What is the scope of robotics? Who are going to hire robotics engineers, and who are the major players in robotics domain? So when we say major players, the big companies are ABB, Fanuc, and KUKA. These are the major companies which are producing robots and also which are uh, having a lot of openings for robotics engineers. Other than this, in India, if you are asking, like a lot of startups and well-grown companies will be there. Like I can see in the space of warehouse management and all, you can see Unbox Robotics. You can see in construction industry, if you want, you can see Origin is one of the company which is working for the US construction industry, which companies, the companies developing some robots, mobile manipulators, which is a combination of mobile robots and manipulators for the construction industry in the US. And there is another company called SynLR. I don't know how to pronounce it. So that is one of the company working in the advanced robotics stuff. There are a lot of research organizations working in soft robotics and all. So there is a wide variety of opportunities in this field, and the good thing is this time IIT Madras, I guess, has released a new paper called for robotics and automation in GATE 2027 as well, so that robotics people can now write robotics and automation in the GATE and do their MTech in the Indian Institute of Science, such big uh, colleges and all. And as I mentioned, that AVs, autonomous vehicles, are much more. We can see those majorly in America or China or in Japan. So, but the thing is, the development is happening in India as well. You can see Minus Zero or Video Autonomous Technologies are building buggies, building AV software stacks. Even the Waymo has its, uh, I think, the technical, what is that, facility in Hyderabad, and development facility in Bangalore as well. So there's a lot of opportunity for robotics people in this area. So with this, I'd like to conclude my presentation on robotics. So whatever I knew, and with the little experience that I had, I presented it here. So hope this was very much insightful to you guys. Gave some uh, what do you say? Uh, Gave some knowledge to you guys. So yeah, with this I conclude. Thank you for the community that allowed me to speak about Robotics India Space Week. Uh, Thank you to the director, the organizers, and everyone. Thank you very much. Yeah, if you guys have any questions, you can ask me. Uh, I think.
Thank you, sir, for such an insightful session. Now we'll move ahead towards the Q&A.
Okay. So I can see some of the questions in the YouTube live, like
Uh,
China is rapidly advancing in
yes,
robotics.
sir.
Yeah, for an Indian robotics student, is China a good option for higher studies, internships, or work? Of course, definitely. China, Japan, or America, even Germany, all these countries have well, I mean, established research centers, and I mean, China is majorly leading in robotics. Actually, if you see, they have defense-related robotics projects, and I think they have deployed many robots in their defense as well. So it's going to be really worth being a Indian robotics student, being in China, going for China for higher studies.
Thank you, sir, for that answer. So the next question is that what are the core technical skills and tools that are sorry, sir.
The core technical skills and tools that a robotics automation student should master to become industry ready.
Sir, am I audible now?
Yeah, you are audible, but I could see the question. I will answer
Oh,
it.
all right,
So
sir.
I majorly mentioned all those in my presentation, that you can, if you want to see, majorly, if you want to dive into robotics, for three domains you can focus. One of the domain is design, so where you design the uh, chassis or any component for the robot. So that is the mechanical CAD software you should know, and some analysis related softwares you should know, SolidWorks or anything similar to those. And then if you are interested in electronics related stuff, you have to go for embedded system related technical things. You have to understand how to program a microcontroller, embedded softwares, I mean programming, uh, majorly how to program STM32 or PCB designing if you are an embedded hardware guy. So this is the stuff. If you want to work purely on software, then ROS2 robot operating system is the one which I mean use to develop robots. So and most of the companies in their initial stage will use ROS2. So you can of course learn ROS2, one of the major tools that will help you to land in a robotic software engineering role. So other than that, you can actually learn about computer vision perception related tools, you can go for deep learning, all those RL, reinforcement learning, all these concepts you can learn. So uh, that would be I think this answers your question.
Thank you so much, sir, for that. Sir, we have one more question. That what is application of post-quantum cryptography in robotic security and how to implement it? Could you please explain from the perspective of research?
Yeah, genuinely saying that this is very new to me, post quantum cryptography, so that I might not be the right person to answer this. So I have to explore this regarding post quantum cryptography, how it helps in the robotic security and all. Uh, Majorly, I work on the segment education segment. So we develop robots that are for mostly for students and educators. So that is the reason we kind of don't involve security concepts here most of the time, but it's actually one of the things that we have in our pipeline, that how we can actually secure our robots. It's still in the pipeline. I did not explore much about this.
Thank you so much, sir, for that. Okay. So next question is that where can RA students apply for robotics related jobs, internships, and training opportunities?
Actually, LinkedIn is one of the better platform. You can just explore the tech giants and all, who are there in the robotics field. You can contact a lot many people in that who are working in robotics and get to know about that company and just start applying through. I mean, you will get their email IDs of the HR of that organization and all, right. So I don't recommend any platforms directly through this meet, because I have used certain platforms, but I don't know. Most of the time, I feel you directly contact the HRs. To contact the HRs, you should get to know, okay, how many companies are present which are working in the robotics domain. So to get to know the robotics companies, you have to do a lot of exploration. So LinkedIn is one of the best platforms to explore things and attend a lot of conferences that are happening in the robotics and embedded systems field. So you will get to see a lot of companies participating in that conferences, and you do networking there, and you can get hired easily there through those things.
Thank you, sir, for this answer. Is there any other participant who wants to ask anything? Is there anybody else who has any question? So I think so. We don't have any more questions. Do you have anything to say, or shall I conclude with the session now?
You can conclude.
Like, thank you so much, sir, for such an insightful session. On on behalf of all the participants, I sincerely thank you. Uh, Now I would request all the participants to leave. Thank you, everybody. Keep learning, keep building, and keep innovating. Have a wonderful day ahead.
Okay, thank you. Bye bye.